Fluorine, okay, exactly. All right, what does that mean, though? What is electronegativity? You don't have to give me a formal definition, but what does it mean? What's the point of it? Think of electro for electron, okay? Electrons are negatively charged, correct? Okay, so if you say that fluorine's more electronegative than carbon or hydrogen or whatever, what does that mean? Okay, not necessarily gain it, but what's it doing to the electrons in the bond? Is it sharing them equally, or is it attracting them more strongly? Yeah, so we looked at this, it's been a while, but we said this was our bond. So if we had fluorine is the green here, okay, and we have hydrogen is my hand, okay, and this is a bond with 2 electrons in it. Okay, if I have a hydrogen fluorine bond, okay, is it going to be polar? Yeah, okay, polarity is based on electronegativity. Okay, so if I had a tug of war on this rope, who's going to win the tug of war? The fluorine, right? Okay, and so it's going to attract the electrons. So if you can imagine, there's 2 electrons in every bond. Okay, so are they going to be directly in the center of this rope? Okay, they're going to be pulled where? Towards this way, right? So it's going to be tugging on those electrons, so they're going to be shifted more closely to the fluorine. Okay, so when that happens and the electrons are negatively charged and they get shifted over, okay, we put a partial negative charge on that fluorine, okay, or on the electronegative atom, okay, because it's not sharing equal, it's not neutral, okay, it's got more negative charge because it's pulling these closer to itself. Okay, so that kind of answers this one right here. Okay, so if we have an HCl bond, so same idea, we had fluorine there, instead we have chlorine. Okay, it's still more electronegative, right? Okay, so if we look at labeling here, our chlorine would be partially negative and the hydrogen partially positive, okay, because it pulled the electrons away from it. Okay, these differences in charge, it's called unequal charge distribution, is the reason why things react. Okay, if you don't have this, okay, then nothing's going to happen. Okay, if I place 2 molecules in a flask in the lab and they're non-polar, there's no reactive site is what we call it, nothing's going to happen. There's no driving force for the reaction to occur. Okay, so what happens in reactions, and then what we're going to kind of look at today, is when you have this unequal distribution, okay, then something else can be attracted to this, right? Okay, so just like a magnet, if you have a positive and a negative end, what's going to happen? They're going to be attracted. That's what reactions are on the molecular level. They're the attraction of positive charge for negative charge. Okay, so for example, if I have a water molecule, I'm going to draw its Lewis structure here. Okay. The oxygen would be partially negative, right? Okay, everybody agree with that? Okay, it's also got lone pairs, so it's got lots of electrons there. Okay, so it's partially negative. Okay, the hydrogens would be what? Partially positive. Okay. Okay. So what do you think if I had HCl, which we have this a lot, we dilute it with water, okay, what do you think is going to happen? What's going to be attracted to what here? Do you think the oxygen will be attracted to the chlorine? Mm-mm. Okay. What about the positive hydrogen? Is it going to be attracted to the chlorine? Exactly. Okay, and so what actually happens, so I'm not going to show, this is an acid-base reaction. You probably didn't realize it. The HCl is your acid, the water is your base, and they react, okay, and they form a conjugate base and a conjugate acid, which we don't get into this semester. Okay, but this is the driving force behind it, is that the opposites attract here, okay, the opposite charge. Okay, and then while we're going through this lecture, I want you to think about why does like dissolve like? So we're going to try to answer that today. Okay, and sometimes it takes going back, reading back through this. I'm just going to, of course, deliver the information to you today. And some people get it right away, and some take a little longer. Okay, but really why we talked about this is because this right here, the answer to that is this. Okay, so it's going to be our like dissolves like is because they are attracted to each other. Okay, so those molecules are attracted. Okay, and in the same way that we show here. So that's really the main idea behind it. So that's why I wanted to bring it up before we get started. Okay, we've seen this a couple of times, but if we have a solution, okay, it's homogeneous, meaning that you can see through it. There's no distinguishable parts. Okay, just like we have a salt solution or whatever it might be. Okay, the solvent is present in the largest amount. Okay, the solute in the smaller amount. Okay, and together they make a solution, right? Okay, so be sure you know that terminology. I may ask you, what's the definition of a solvent? What's a solvent? Okay, don't tell me solution. Some reason solvent and solution people get backwards. Okay, solution is both together, or how many ever solutes you have in your solvent. Okay. All right, and this is simple, but I just want to be sure everybody sees this. Okay, if we have, this is one salt solution, so I'm going to make some little dots here. Okay, there's some salt, or let's just say it's just our solute. Okay, and here it's a solid, doesn't have to be. We're going to see that in a minute. Okay, and then I put some water in it, and then of course I'd mix it up. Okay, if I have another solution, okay, same water level. There's my solute. Okay, which one's more concentrated? Okay, what do I mean by concentration? You guys have had given definitions. You've given, molarity, weight percent, percent by mass, mole fraction, molality. Okay, so James is right. Okay, but what do I mean if it's more concentrated? It means it has more what? Not solvent. Solute, exactly. Okay, so I know that seems pretty simple, but we're going to talk about osmosis today as well, and for some reason that gets backwards. People think that, this is more concentrated. Okay, whatever has more solute is more concentrated, just like our sweet tea example. If it's got more sugar in it, what's it going to be? It's going to be more concentrated, right? Okay. All right, so we have a lot of different scenarios. So most of the examples that I've talked about, we've had a solid in a liquid. So our solid has been the solute, okay, just like sodium chloride or salt. Okay, but we can have lots of different scenarios. So we can have gases, liquids, solids. Does anybody know of two gases that are around us all the time that are a solution? What do we breathe? Okay, we breathe, what's our air composed of? Okay, air is a solution, right? It's homogeneous. I don't see, thank goodness, I don't see any distinguishable parts in here, right? Okay, so what's it made of? What's our atmosphere primarily made of? You said we have to have oxygen, so there's one. Okay, do what? Okay, we have a little bit of carbon dioxide. Nitrogen is 78% of our atmosphere is nitrogen. Okay, so we have nitrogen and there's oxygen. We have some hydrogen, but in a lot lower amounts. Okay, so nitrogen is the number one component. Okay, if we have all these different possibilities. We're going to look at some examples. Most all of them are going to form a homogeneous mixture, meaning we can see through it and there's no parts. Okay, but then we do have two possibilities that are always going to give us a heterogeneous mixture. Okay. So here's 7 homogeneous possibilities, and here's 2 heterogeneous possibilities. Okay, so as you look here, we have mixtures of solids and liquids and gases and some examples. So you want to be familiar with these, be able to give an example, okay, of a solid solute and a liquid solvent. We've been using that all the time, right? Salt water, tea with sugar, sweet tea, whatever. Okay, liquid and liquid. So you've we did this in the lab. We mixed methanol and water, or ethanol and water. Okay, so you went through and did lots of examples of that in the lab, and you shook it up in your test tube to see if they were miscible or not. Okay, in a carbonated beverage, we have a gas and a liquid. Anybody know what's in your Mountain Dews or Cokes? What gas is in there? Anybody? Carbon dioxide, exactly. So that's what gives it the fizz. All right, so when you take off your top, and we'll look at this again later, so you take it off, it makes that noise, that fizz, where pressure is built up in there, you've got a gas. Okay, but if you leave the top off your drink for, a few hours or however long, what happens to your Coke? It gets flat. Okay, that's because all the CO2 gas escaped. Okay, so it no longer has that fizz anymore. Okay, or the bubbles, I guess if you think of it that way. Okay, does anybody know what this is here? The dental amalgams. Okay, those are just fillings. All right, so this has changed a lot over time. Used to, your fillings were mercury, which is liquid mercury, and then combined with some kind of solid metal. Okay, now they're, of course, mercury we know is poisonous, so now they're changing that. So a lot of the fillings are porcelain and different things like that. But that's what this is talking about here, is if you had liquid mercury with another solid. Okay, an alloy, just like steel. Steel is iron and carbon, so it's a mixture, okay, of two solids. Okay, so a lot of your metals there. Brass is also one, mixture of copper and zinc. Okay, this one's a little confusing, a metal pipe, a gas in a solid. This is talking about when you have natural gas flowing through a pipe. Okay, so you have a solid pipe and then the natural gas. Okay, air, example of a gas and a gas, right? We got nitrogen and oxygen and hydrogen all combined, and it makes a solution. Okay, if you have a solid and a gas, okay, this is going to be heterogeneous, so they're going to be separate. So just like dust in the air, so if you kick up a bunch of dust, you can see it. It's in the air, it's mixed with it, but yet you can see both parts. Okay, and then liquid in a gas is like clouds or fog. Okay. So in lab and other times we've mentioned that like dissolves like. Okay, so we're going to look at why. It's called the dissolution. All that means, that word, all it means is that two things are soluble in each other. Okay, so here we're going to look at a solid and a liquid. Okay, then we're going to look at liquids and liquids, and then gases and liquids. So we're going to look at all those scenarios. Okay, and if you get really one of them, then you're going to get the rest of them for the most part. Okay, what happens for two things to be soluble is they have to be attracted to each other, especially when they're polar. Okay, and this attraction, like over here that we showed earlier, that's what makes like dissolve like. Okay, it doesn't just happen just because or just a coincidence. Okay, there's actually attractions that occur to make this happen. Okay, so if you take salt water, okay, so keep using that example over and over again. Okay, but sodium chloride, is that an ionic compound or covalent compound? Do you remember? It's ionic, right? It's a metal and a non-metal. Okay, so if you think about our metal and non-metals, so I'm running out of room here. Okay, we have sodium chloride. Okay, sodium forms a what charge? +1, right? Because it's in group 1. Okay, and then chloride always forms a -1. Okay, so your ionic compounds are extremely polar. Remember, they have the largest electronegativity differences. Okay, that's because they form a full positive, bless you, and a full negative charge. Okay, so remember they break down into ions. Okay, all right, but if we have it in water, so I drew water over there. I need to get me a better pen here. Okay, so let's see. All right, is water covalent or ionic? It's covalent, right? It's two nonmetals. Okay, so it doesn't break apart into its ions like an ionic compound does. So we already said we have a partial negative and a partial positive. Okay? Ionic compounds like sodium chloride are pretty strong compounds, right? Because this and this is really attracted to each other, right? So it's real attracted, so that's why we write it like this. Okay? But in water, somehow it's soluble. And you guys saw this in the lab, right? You stirred it up or swirled it around, and eventually you got it to be soluble in each other. Okay? So in order for this salt, okay, to be soluble in water, you had to somehow break it apart into its ions. Okay? So even though this is a strong compound, it is attracted to the water molecule. Okay? So what happens? So this is the main thing here. Okay? If you can, sorry, what am I looking at here? Yes. Here's your solute-solvent attraction. Okay, so the salt here is our solute. Water is our solvent. Okay? In order for these to dissolve in each other or be soluble, they have to be attracted to each other. So something has to happen, and these have to be attracted to each other in order for them to be soluble. Otherwise, if they're not, they're just going to separate from each other, and you're going to have those two layers, like you saw in your test tube or whatever you're in. Okay, so what happens is this charge, these charges are attracted to the charges of water. Okay, so remember we said water is polar, right? Okay. All of our ionic compounds are polar. They're very polar. Okay, bless you. Okay, so like dissolves like, and what happens is they have to be attracted to each other. Okay, so if you look over here, you have a partial positive, a partial negative. Okay, so what do you think the oxygen is going to be attracted to? It's partially negative. Yeah, the sodium, exactly. So what's going to happen is water is going to come in and it's going to solvate, okay, that sodium ion and the chloride ion, okay, depending on the way it turns itself. Okay, so around the sodium, okay, it's going to be attracted. So I'm just going to write, it's not bonded. I'm just writing a little dash for it's attracted. Okay. So if you can imagine, there's hundreds of these. I'm just showing one interaction. There's hundreds of these. So they're going to all be around, so we can draw another one here, the sodium. Okay, so this is what's showing here. So that red is the oxygen, and the two white are the hydrogens. So it's turned inwards with its oxygen attracted to the sodium, so it pulls it apart from here. It's all together. Here you have your sodium chloride as a solid. Okay, so the water comes in, it's attracted to the ions, and then it solvates it. Okay, so those positive, negative attract. Okay, and so the same thing for the chloride. Okay, so water has a positive portion as well. So the hydrogens are going to be oriented towards the chloride like so, because positive and negative attract. Okay, and so the chloride, as you notice here, see how the hydrogens are pointed towards the chlorine? Okay, that's because the hydrogens are positively charged, right? And they are attracted to the negative charge. Okay, so I've already explained this. Here's a little bit more, but that's the electrostatic force. All that means, it sounds maybe a little bit like a hard terminology, but it's not. All that's talking about is positive attracted to negative. That's all that means, okay? And we know what's positive and what's negative based on understanding electronegativity. Okay? For nonpolar substances, it's a little bit different. When you have a nonpolar compound, we'll look at those here in a second, there's no charge. Okay, so there's no distribution of charge. And so it's simply described as two nonpolar substances just kind of slide in between each other. Okay, due to no forces at all, they're able to just slide in between each other and be soluble. And we'll look at that a little more too. Okay, here's two nonpolar compounds. Okay, one thing you have to remember, and this was one of the most missed things from exam 2, I believe. I guess it was on exam 2. Is that hydrocarbons are nonpolar. Okay, so I have that right here in big underline. People will still miss it anyways, but it is nonpolar. Hydrocarbons mean that it's only composed of carbon and hydrogen. Okay, so up here I have hexane, but all you have to look at, you don't have to know that name. You just have to look at the compound. Is it all carbon and hydrogen? Then it's nonpolar. Okay. All right, here we have two iodines that are bonded together. We call this a solid iodine. Okay, so do y'all agree that it's nonpolar? Okay, when you have two of the same atoms bonded together? Okay, right, because there's no electronegativity difference, right? They're the same molecule, or same atom. Okay, this is the exact thing that we did in the lab when I did the demonstration, and I had the test tube and I had the water and the iodine in there, and then I shook it up, I added the hexane, shook it up, and you saw that pink purple color move to the hexane layer. Okay, this is what we did in lab, and it showed us that the iodine was soluble in the hexane, not in the water. Okay, and that's because like dissolves like, right? So hexane and iodine are soluble in each other. All right, if you look here about this question, okay, do you think bromine would be more soluble in water or in pentane that has a C5H12 as its formula? Pentane? Everybody agree? Exactly. Okay, bromine, Br2. So if we looked at that bond, if these are both, my hand and this are both bromine, okay, does one pull harder than the other? No, they pull the same. So they share equally, meaning there's no electronegativity difference. And remember, electronegativity is based on, or polarity is based on electronegativity, so it's nonpolar. There's no shift in electrons. Okay? All right, so pentane is another hydrocarbon, so it would be soluble in that. Okay, before we move on to the liquids, so liquids soluble in liquids, we're going to talk about a interaction, and it's a special case of a strong dipole interaction, but we'll look at what that means. Hey, but it is not a true formal bond, okay? Actually, do not like the name of this. It's called hydrogen bonding, and that's what it's universally known as. Okay, but that's really confusing to students that don't, first seeing this, because they think it's a new bond that we're talking about. Okay, the only bonds, true bonds that we have, chemical bonds, are our ionic and our covalent bonds. Okay, hydrogen bonding is a strong interaction, but it's not a true bond. Okay, so we'll see that. Okay, hydrogen bonding occurs among polar covalent molecules. This is where if you need to go back and review Chapter 7, I would suggest it, because it's all about electronegativity and polar covalent and nonpolar covalent. Okay, it's when you have a hydrogen, hence the word hydrogen bonding, okay, bonded to one of three highly electronegative atoms. Okay, and these are fluorine, nitrogen, and oxygen. Okay, so if you look at your periodic table, okay, those are next to each other in the second row. So it's fluorine, nitrogen, oxygen. Okay, some students accidentally replace this with fluorine, chlorine, and bromine. Okay, those do not hydrogen bond. Okay, so it's fluorine, nitrogen, and oxygen. So you want to know those three atoms and be sure you don't get those confused with anything else. Okay, hydrogen bonding is actually what we showed right here, over here, before we ever got started. Okay, it is a strong electrostatic, meaning positive charge is attracted to negative charge, or vice versa. Okay, and it happens with atoms that have a hydrogen bonded to an oxygen, nitrogen, or a fluorine. This, of course, doesn't have to be all of them. Okay, it's just one of them. Okay, so I'm going to draw this, or show it first, and then we'll draw it. Okay, so here we have HF. Okay, it can hydrogen bond because it meets our definition. HF has a hydrogen and it has a fluorine. Okay, so hydrogen bonding occurs between a hydrogen, when it has a hydrogen, and a fluorine, nitrogen, or oxygen. Okay, and then we have methanol. So methanol is our structure underneath here. All right, so when we label our HF bond, the fluorine has the partial negative because it's more electronegative. Okay, and the hydrogen has a partial positive. Okay, when we go down here, our oxygen has the partial negative and hydrogen partial positive. Okay, this right here is just carbon and hydrogen. Okay, there's no charge here. Okay, remember we consider our carbon and our hydrogen to have the same electronegativity or very similar, so we don't have that unequal distribution. Okay, this right here in red, that's what we call our hydrogen bond. Okay, this is a strong interaction between molecules. Okay, so let me show you a difference here. Okay, this right here is an interaction between two different molecules. Everybody see that? Okay, a covalent bond is this right here. Okay, a covalent bond is between two atoms, okay, bonded together. Okay, this is an interaction between two totally different molecules. Okay, so that's a big difference. So some students want to make it a true bond and put it in there. Okay, it's just an interaction. So if you place HF in methanol, okay, so we have two liquids is what we're thinking about here. Okay, they're going to be soluble in each other because they're going to hydrogen bond. Okay, and this is a strong interaction. Just like we said, we have to have interactions for like to dissolve like. Okay, and this is just very strong. It's still not as strong as a true bond, but it's the strongest of our what we call intermolecular attractions. Okay, and that's because we have partial positive attracted to partial negative. Okay, this is just one hydrogen bond that we're showing. Okay, if you actually place, put 10 milliliters or whatever in your test tube, there are hundreds to thousands of these molecules. Okay, so they're all just hydrogen bonding together. Okay, so if we wanted to, we could extend off of this and show another hydrogen bond. Okay, so if we have a partial positive charge here, and we had another HF molecule, okay, if I had room, we could keep extending and extending and extending as big as this board would allow us to, okay, because that's what would be happening with all the hundreds and thousands of molecules that we would have. Okay, so we want to do another one here. Let's do another hydrogen bond. Okay, so what would this hydrogen be attracted to if we're looking at it with the methanol? It's partially positive, so what's it going to be attracted to? Oxygen, exactly. So there's our partially negative oxygen. There's its lone pairs. I don't know if you can really see those very well, but I'm kind of drawing it upside down here, but okay, partially positive. Okay, we could extend over on this side if we wanted to. There's another hydrogen bond. Here's a hydrogen that's partially positive. There's our oxygen. Okay, so you'll want to practice these. You have to be able to draw these on the exam. Okay. What you're also going to have happen is you're going to have HF and methanol, either one. They're also going to hydrogen bond with themselves. Okay. So if you have two HF molecules, it doesn't look like a hydrogen. Okay, they're also going to hydrogen bond with themselves. Okay, here's water. Okay, water hydrogen bonds with itself as well. Okay, so there's the oxygen. Okay, so it's showing you how it does that. There's the oxygen, hydrogens. So we'll just look at one. Okay, what this arrow means is that the hydrogen and the oxygen are attracted to each other. Okay, so the main thing here is you have to be able to label your atoms as partially negative or partially positive based on their electronegativity. So the closer they are to fluorine, they're going to bear a partial negative charge. Okay, hydrogen's always partially positive. Okay, it's not ever going to be partially negative. Okay, and then you orient the molecule to where it hydrogen bonds. Okay, here you're showing two different molecules. Okay, or it can hydrogen bond with itself, right? Okay, so that's all that is. And that dash there just shows it's not a true bond like we would draw here. It's just an attraction. Okay, when these attractions occur, it makes them soluble or miscible in each other. Okay, so this is what I just said, but when you're looking back studying, we'll see this. So our like dissolves like rule for our polar molecules and for liquids and liquids. Okay, we use the term miscibility, so you'll see this on your key term sheet. You can only use the term miscibility when you have two liquids. It's just a term that you have to know. Okay, but if you've got two liquids, we say they're either miscible or immiscible in each other. And so here it shows, I believe here we have, just like the last slide, we have water, and then we have, or we had HF in the last one, but here we have water and methanol. So it's showing you where the hydrogen bonds are, where it has those arrows. Okay, so you just want to be sure that you can redraw this. So I would practice, drawing what's up here, being sure you can illustrate this as well. Okay, this is still true for our nonpolar molecules. Okay, but there's no attraction. There's no charge in a nonpolar molecule because it has no electronegativity difference. So they're nonpolar, and essentially they just kind of slide between each other. Okay, so this hydrogen bonding is when we have polar liquids. Okay. So looking at these nonpolar molecules, first we're going to look at these two. Okay, so benzene is C6H6, and this is this Lewis structure. So you may or may not know how to draw that, and that's okay. But the thing that you would look for is the fact that it is a hydrocarbon, right? Okay, do you see anything else but carbon and hydrogen? Okay, so if we have a hydrocarbon, it's always nonpolar, right? Okay, over here we have hexane again. Okay, so I could draw out more and more and more carbons. I could have decane, or that's 10 carbons. It doesn't matter. All you're looking for is the fact that it's composed of what? Carbon and hydrogen only. Okay, if I throw in an oxygen, then it's not a hydrocarbon anymore, right? Okay. All right, but what about this? Okay. Does it look nonpolar or polar to you? Okay. So if I look at just one bond, I have a carbon-chlorine bond. So we've learned so far that chlorine's more electronegative than carbon, right? Okay, so you would think that this would be, or I would, if I was in your shoes, I would think that this would be polar. Okay, but yet I have it on the nonpolar slide, and it's not a typo. Okay, so I'm going to show you a difference, and we're going to see this a lot on Wednesday. So this is not going to be, you'll pick this up pretty quick on Wednesday with our lab. Okay, but if we have, so I need 3 volunteers here. Anybody? You would be one? Tanisha, do you mind? Okay, Blake. And I'll be the other here. Okay. All right, when we just have, if y'all will just kind of hold yours down actually for right now. Let me demonstrate the first part. Okay, don't look at them. Just look at, whoop. Get almost. There you go. Okay, so don't look at their bonds here. We're just going to look at this bond right now. Okay, so I have a carbon, that's what's going to be in the middle, okay? And then I have, we're all chlorines, right? But you're looking at this one right now. Okay, when we look at just this single bond, we would think that this would happen, right? You let go for a second. Okay, we would think that this is going to happen, right? I'm going to pull harder on this bond, right? Everybody agree with that? That's what you would think. Okay, because we're all chlorines, okay, so are we backwards here? Okay, let's flip you and me real fast. Okay. All right. So we're looking at a shift, right? That's what polarity is that we have a shift, an unequal distribution of charge. Okay? If we're all chlorines and we all pull at the same strength, so everybody pull. Nobody pull harder than anybody else. Well, y'all are pulling too hard. Okay. Right here. Do we have a shift? Did the carbon, is it going to shift towards her or towards him or towards me or towards him? Because we're all pulling at the same strength, there's no shift. Okay? So that means this molecule, even though I have one bond that is polar, the molecule is nonpolar because we're all pulling at the same strength. Therefore, the carbon is not being, it's not really the carbon, it's more the electrons, is not being shifted one way or another because we are all pulling equally. Okay? Now, let's say that Abdullah is a fluorine, okay? And we're not carbons, we're still chlorines, okay? So we've got carbon, chlorine, 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 and now a fluorine, okay? Do you think this molecule is going to be polar? What do you think? Who pulls harder? Okay, so you pull us. Okay, so we need to stay back here. You pull. Look how it's shifting. Okay, what we're creating is what we call a dipole. And a dipole means we have a charge distribution towards Abdullah. He is pulling the molecule and pulling electrons towards him, which shifted everything else. And it actually, if you notice, go back to our other one. This is a certain geometry. It's called tetrahedral. You're going to learn that Wednesday. But when we shift towards him, okay, we just changed the geometry, didn't we? See how everything kind of went like this and pulled towards him? Okay, so that would be polar. Thank you, guys. Okay, so the idea here, if you have all the same molecules or atoms around a central atom, okay, then it's going to pull at the same strength and leave it nonpolar. Like I said, we'll have lots of examples of this on Wednesday. Okay. Before I move on, though, if you have a lone pair, okay, so if you look at water, we've established that water is polar, right? Okay. However, it has two hydrogens on each side. Okay. But when you throw in lone pairs, that makes this very polar. Okay, these lone pairs matter. Here we had, all chlorines. Here we have two hydrogens, but then we have lone pairs. Okay, so these lone pairs pull hard on the atom, and they make it very polar. Okay. We still have the same rule for like dissolves like, but we have a couple more examples when we are dealing with gases in liquids. And we're just going to look at gases in water. That's all we're going to look at, and that's all we do for Chem 111, because gases can act a little bit different sometimes. So we're just going to look at if we had a gas in water. Okay. Our like dissolves like theory is going to be the same. If we have a polar gas and water's polar, right? Okay, then they're going to be soluble in each other. Okay, so what you have to be able to recognize is what's polar. Okay, so if I have, let's say I have, HF. Okay, HF gas. Is HF polar? Is that a polar gas? Yeah, it's very polar. It's actually a very dangerous gas as well. Okay, so it's polar. So is it going to be soluble in water? Does like dissolve like? Yeah. All right, water's polar, HF's polar. In the gas form, it doesn't matter if it's in the liquid or the gas form. Okay, it's going to be polar as well. Okay, but we also have two more compounds that I'm going to add to this, and this is on your key term sheet as well. Okay, but some gases can react with water and be soluble, okay, even though they are nonpolar. Okay. Okay, so the two nonpolar gases that I want you to know are CO2 and SO3. Okay, think about CO2. Okay, if you drew the Lewis structure, you have double bonds to oxygens like this. Okay, based on what we just said, if carbon's in the middle and I have two oxygens pulling at the same strength, is this a nonpolar or polar molecule? Two oxygens pulling at the same strength. Am I going to go like this or this? No, I'm staying right here in the middle. So it's nonpolar. Okay, CO2 is nonpolar. Same thing with SO3. You've got three this time, so you're going to have a double bond. So oxygen, oxygen, and oxygen. Okay, and all the oxygens are pulling at the same strength, so it's going to be nonpolar. Okay, but these two gases will react with water and be soluble. Okay, so that's why they're different. Okay, so they're an exception to our like dissolves like rule, because water's polar, but yet CO2 will react with it and form a weak acid known as carbonic acid, which it does. This happens in your blood, so thank goodness this does occur. Okay, and then goes on to form your hydronium, which don't worry about that too much. This is an acid-base reaction there. Okay, the top here, I have HCl, HBr, and HI are all soluble in water. Okay, and I show a acid-base reaction, and like I said, we're still haven't gotten to those. Okay, but the main idea is, you know, HCl, HBr, and HI are all polar, right? Okay, so they're going to be soluble in water, which is polar. Okay, so the only exceptions here are the CO2 and the SO3 that you have to know, because they're nonpolar, but yet they're soluble in water. Okay. All right, we're thinking of gases, so I'm going to give you a few more examples of this, just to be sure everybody gets it. Okay. All right, so let's do a quick one. So we have gases, so we have water in gas form. Okay, so we have H2O, gas. All right, and this one's up there, but I'm just going to... Okay, so if I gave you these two, okay, what's the first thing that you're going to do to try to determine, are these soluble in each other? Okay, I think I'd probably want to label them, right, as polar and nonpolar, because I know like dissolves like, right? Okay, so I'm going to put, we know water's polar. We saw that in the lab. Okay, and what about HBr? Is it polar or nonpolar? Okay, it's polar. Okay, we have a hydrogen bonded to a bromine. Okay, is bromine more electronegative than hydrogen? Yeah, so we're going to have a polar. Okay, so polar and polar, and they are soluble. So we would put S for soluble. Okay, what about if we had water vapor and nitrogen gas? Okay, water's polar. Nitrogen is two nitrogens bonded together, even though it is a triple bond there, but two nitrogens bonded together is nonpolar, right? Okay. So would these be soluble or insoluble? Insoluble, exactly. All right, so you'll have to do some of those on the exam. Just look at two compounds. You have to be able to determine, are they soluble or insoluble by their polarity, because like dissolves like. Okay. All right, and then CO2 and SO3 are exceptions. So if I put, water vapor with CO2, you just have to know CO2 reacts with it. You don't have to know the equation or anything, but you would know that those would be soluble. Okay, when we're looking at gases, pressure becomes important to us, and we'll spend a lot of time talking about gases and pressure in the next unit. Okay, but if we have a solid or a liquid, they're not compressible, right? So I can't compress this solid down any further. And for the most part, a liquid is very, it's pretty incompressible as well. Okay, but for gases, this is not the case. Okay, so if we increase the pressure, okay, of something, we can also increase the solubility. Okay, so we can push those gas molecules into solution, say with water in our example here. Okay, so just like your carbonated drink again, with CO2 in it, okay, it's compressed into a can or a bottle or whatever it is. Okay, so the more you compress it and take those gas molecules and compress them into a container, those CO2 molecules are going to be soluble in the water and the syrup or the aspartame or whatever else is in your drink. Okay, but when you open it up, then what happens? You release the pressure and the CO2 leaves. Okay, and so then it's not as soluble, right? Because gases want to float around wherever, fill up the space that's around them. Okay, so here's an example. If we had a vessel here, and so the pink molecules here, or pinkish red molecules, okay, that's our solute, and we'll just say these yellow ones are water. Okay, so if we have a vessel and we have it, it's about yay big here. Okay, we have about 3 solute gas molecules in solution. Okay, but if we increase the pressure, okay, so now we have about half of that volume. Okay, then what happened to our solution here? Do we have more gas molecules soluble or less? And more, yeah. So we pushed about, looks like we have about double. Okay, so now we have 6 of those pink molecules compressed. Okay, and this is actually a gas law, but we're not going to get ahead of ourselves. But I just want you to see that pressure makes a difference in the solubility of 2 gases. Okay, so if you increase the pressure, okay, then you're going to increase the solubility of those 2 gases. The next thing we're going to talk about are colloids. So you'll have to know this definition. It's on your key terms as well. Okay, and the reason we talk about it is it's because it's unique. It's an intermediate mixture. It is heterogeneous. Okay, so it's not a true solution. Okay, but it has a particle size between a true solution and a suspension. Okay, so first we kind of need to talk about what each of those mean. Okay, a true solution is like that of when we mix methanol and water. Okay, they're both polar. They're a true solution. There's no heterogeneous particles, and it's pretty much see-through when we make that solution. A suspension is 2 things that are not soluble in each other whatsoever. Okay, so that means that they suspend away from each other and they are completely separate when you try to mix the 2. Okay, a colloid is a mixture between those 2. Okay, it's not a true solution, okay, because it's not clear, it's not completely see-through. You can see the particles. However, it's not a suspension either. It's not completely separated. Okay, so we use colloids all the time, so we're going to talk about that here in a few minutes. Okay, but a colloid, something like smoke, fog, paint, milk, mayonnaise, okay, shaving cream, clouds. So sometimes the examples give you more of an idea of what we're talking about than even the definition. If you think about mayonnaise, some people, that grosses people out thinking about, don't like mayonnaise, but but it is not a true solution, right? It's kind of, it's got a texture to it, okay? But it's also not completely suspended out. Okay, so what's mayonnaise? What's it made of? Okay, that's a great point. It does have egg in it. Okay, but what else does it have? Anybody know what it is? Okay, it's water and oil. Okay, if you take water and oil, what happens when you mix the 2? Do they mix? Absolutely not. They are a suspension, meaning water is going to form one layer, oil is going to form the other layer. Okay, so they are not whatsoever attracted to each other. Okay, so water is polar, right? So oil has to be nonpolar, right? Because they completely separate, okay? But if that's the main component, that's all mayonnaise is, minus one thing, and that's what James just said. He said there's egg in it, okay? The egg is the biggest component as far as keeping it together, okay? If you just have oil and water on the shelf in the grocery store, then it's going to look separated into oil and water, and it's not mayonnaise, okay? But if you add egg, okay, the egg is what keeps it in suspension, okay, and that's what makes it the mayonnaise. Okay, so that brings us to this point that we just talked about. I'm going to come back to that just because we got on to the mayonnaise here. Okay. Mayonnaise is a hydrophobic colloid. Hydrophobic means it's water-hating. That's also on your key term sheet. Has a phobia against water. Hydrophobic, pretty easy to remember. Okay. Hydrophilic means it's water-loving. Okay, so what I mean by that is if it's water-hating, it means it's not attracted to water. Okay, so if water's polar, something that's hydrophobic must be what? Nonpolar, right? Okay, they don't like each other. They're not attracted to each other. Okay. All right, so we just said that the vegetable oil and the water are the main component of the mayonnaise. Okay, but the egg is the most important part. Okay, the egg is what we call the emulsifying agent. Okay, you've got to know that definition as well. Okay. The egg is what keeps the oil and water together. Okay, otherwise they're going to be separated because they're polar. One's polar and one is nonpolar. Okay, so the mayonnaise as a whole, the whole container there or whatever it is, that is your colloid, okay? But the egg is the emulsifier, or the emulsifying agent. Okay? All right, just to show this, we're going to go back real quick. Hydrophilic means water-loving. So this is when you have a colloid. So this is actually hemoglobin in our blood, okay? And up here we have, I'll draw in the molecules here. Okay, so this is a protein that we have. Okay, these are hydrogens. Okay, here's water. Okay. Hydrophilic means water-loving, meaning there's an attraction to water. Okay, so here's our colloid. This is a protein that's in our blood, like I said. Okay. If we look here, we have a nitrogen, and then our hydrogens are partially positive. Oxygen is partially negative, so they attract. Okay, because they have that attraction, okay, that means they're soluble. That portion of the molecule is soluble, okay, and so we call this hydrophilic, okay, because we have that opposite charge attraction. Okay, mayonnaise is nonpolar. Okay, we consider it to be nonpolar. Okay, so it's a hydrophobic colloid. Okay, so that means it's water-hating. Okay, so going back to the emulsifying agent. Okay, soaps, detergents, anything you use, whether for dishes, shampoos, all kinds of, antibacterial soaps, anything like that. These are all what we call emulsifying agents, just like the egg. Okay, so we're going to look at what a soap molecule looks like and talk about that. Okay, so soaps are usually just long fatty acid chains. So we're going to look at what that is, the structure. Okay, sodium stearate is the example of a typical soap. Okay, and that's the example that we're going to show. Okay, keep in mind though that there are soap chemists. Okay, so they change small things, small atoms, or not really small because it makes a big difference, but they change and go through and change little portions of the soap molecule, and that makes, a difference between dishwashing detergent versus the shampoo that you put in your hair. Okay, there's a difference, right? Anybody ever washed your hair with dishwashing soap? Makes it pretty rips everything out, all of the oils. Okay, so there's a big difference. And from your laundry detergent. Okay, so this is, it's a growing field, really, to be able to look at a soap, change it in some sort of way, and make it better or make it for, one thing versus for something else. Okay. The soap is not a colloid. Okay. Remember, the colloid is our nonpolar, our polar substance plus the emulsifying agent. That makes the colloid as a whole. Okay. So for an example of soap, okay, if you are cleaning dishes, okay, you've got water usually running, right? You've got your water running. Okay, water is polar. Okay, then you've got your soap. Okay, so your dishwashing soap that you're using. Okay, and then on the plate that you're cleaning, you have oil and grease. Okay, that's why you're cleaning it. Okay, so all of that together is your colloid. So you make a colloid every time you clean something, or when we're cleaning in the lab. Okay, so the oil and the water are obviously not attracted to each other, right? Okay, so if you have something that's extreme, like you just fried some chicken or something, and you've got a lot of oil in a pan. Okay, so if you put it under the water and just sit it there, it doesn't clean up by itself, right? I mean, you can scrub it, but most of the time the oil there's going to be residue of oil. Okay, you put soap in there and you scrub it with the soap, the water, and the oil, then you clean your dish, right? Okay, so oil and water, the reason they don't clash is one's polar, or they do clash because one's polar and one's non-polar. Okay, you put the soap in there, and that what makes the two become a colloid. Okay, now they're not suspended, okay, and they're together. So it basically coats the particles to be able to keep them in suspension together. Okay, this is one soap molecule. Okay, there are thousands when you even use, or hundreds when you use a tiny drop of soap. Okay, but the main thing that is so important about this molecule is that it has a nonpolar portion and a polar portion. Okay, so if you look at the tail, so we consider that oxygen, these double oxygens and this positive, negative charge, that's the head of the molecule. Think of it as like a snake. Okay, all of this tail, okay, what is it composed of? What's it made of? Carbon and hydrogen, which is non-polar, right? We've already stated that. Okay, over here we have a full positive and full negative charge. What does that tell us about polarity? Is that polar? Do you have a positive and negative charge and they attract? Absolutely. So this is our polar portion of the molecule. Okay, soap is not going to be soap unless you have a polar portion and a non-polar portion. Okay, so over here we call this the hydrophobic portion because we know that non-polar molecules, this hydrocarbon portion, is not going to be attracted to water, right? Because water is polar. Okay, however, our polar head is attracted to water because it's polar and so is water. Okay, so you have to have both of these portions for soap to work. That's what makes soap soap. Okay, so what actually happens is you have, hundreds, you have a large number of all these molecules that orient themselves together. Okay, so I'm going to show that here on the next slide. Okay, and they put their hydrophobic tails, so that's this part, are pointed in. So when there's hundreds of these, they point the tails in, and then the polar portion towards the outside. Okay, and this becomes what we call a micelle. Okay, so soap molecules, they cluster together basically, and they form micelles. Okay, so this right here is just the molecule I just showed. It just doesn't have all the carbons and stuff in there. Okay, then we take this molecule and we put, a large number of them, okay, together. Okay, so the inner portion, okay, of the micelle is the long hydrocarbon chain. Okay, that's where the oil and grease is going to be absorbed, right? Because we have a nonpolar portion. Okay, and so the oil is nonpolar. Okay, so we already said we have soap, oil, and water, and we need to get them into suspension together and make them a colloid. Okay, so when you're cleaning your dishes, the nonpolar portion of the micelle, okay, which is the hydrogen-carbon chain, okay, that's going to dissolve the oil because they are nonpolar and oil is nonpolar. Okay. Out here, this is where you have the polar head of the soap molecule. Okay. All right, so what do you think it'll be attracted to? The water, yeah. So we have the oil and we have the water. Okay. So the oil and grease is absorbed into the interior, okay, the nonpolar interior of the micelle. Okay, so that's where the oil and grease from our pan earlier. Okay, that's where it's absorbed. And then the polar portion keeps it in suspension with water. Otherwise, you would just have the oil and grease and the water separate, and you wouldn't be able to, scrub or wash the oil away. Okay, and so the polar outer portion there is what prevents the water from separating, okay, in your colloid. Okay, so you have to have both. That's the important part, a polar portion and a nonpolar portion. Okay. Let's see how much time we have here. Okay, the last part of this chapter, we'll just introduce it and then we'll finish it up on Wednesday, but is osmosis. A lot of you have probably heard of osmosis before. Okay, so it's not really, hopefully not anything you've ever heard of anyways. Okay, but the idea is that the solvent is going to pass from low concentration to high concentration. And when it does this, it creates pressure. Okay, I think of it as, if you have a membrane, which we'll see here in a second. So if you have a membrane, your low concentration is going to flow to the high, meaning it's going to dilute it, right? So high concentration would mean we have more of those little solute, molecules that I showed earlier. Okay, it passes through a semi-permeable membrane, okay? And examples of this would be cellophane, saran wrap, our skin, and cell membranes, okay, are all semi-permeable membranes. So this is where only specific molecules will pass through, okay, and osmosis will occur. Okay, here's an example. So we have a sugar solution in here. Okay, so where's our low concentration area? Is it here or in the tube? Okay, remember we got to think about what's concentration mean. Here's a sugar solution. Okay, this is concentrated, right? It has solute molecules. Okay, water is going to pass from low to high. Okay, here this rubber band is used as a semi-permeable membrane. So what would happen is, if you notice, here's the level at the start. Then water is going to diffuse through. It's going to flow from low to high. And now look at our water level. Okay, it went all the way up. Okay, so be sure you can tell. Here is our solute concentrated solution, okay, with sugar in this example. Okay, we have a sugar solution. Okay, so there's numerous pictures showing this, but it's all the same. Here you have your membrane. Okay, this side is more concentrated. See how we have these big molecules here? Okay, and so water, H2O, is going to flow from low to high concentration. Okay, yes. Yeah, it could be. That's more, you don't have a membrane in that. That's actually like just absorbing the water because you're placing it on, on the water. Okay, this is talking about if you have, you have this membrane like your skin or a cell membrane, and on one side you have a concentrated solution, on the other side you just have water. the water is going to diffuse through the membrane to the side that's more concentrated. Okay, but somewhat. I mean, a paper towel is more concentrated with, you know, the polymer or whatever it's made of. So, but you're not actually just like touching and absorbing it. So only a few things can actually do that: your skin, cell membranes, and saran wrap. So, okay, we still have 5 minutes, guys. So hang on. Okay, here's a video you can watch of it. So we'll do that on Wednesday, and that may show you may be able to see it better there. But same idea, if you have a sugar solution or whatever it might be, you're going to, the net flow, and it's going to create a pressure when this happens, is going to be from the side of the low concentration, usually meaning just water or very few solute molecules, to high concentration. Okay. Okay, I may actually show this. Y'all are so antsy. I'm going to show it anyways. There we go. All right, we'll end with this, and we'll talk about reverse osmosis. It actually has more like practical everyday use that we can use. Most of the osmosis occurs, you know, in our bodies, which is very important, but